Hello everyone and welcome to AISC's webinar, Get Fired Up, What Structural Engineers Should Know About Fire Design, presented by Maria Garlock. Today is February 22nd, 2017. My name is Christina Harbour and I am with AISC's Continuing Education Group. I'll be moderating today's presentation. I want to introduce today's speaker. Maria Garlock is an associate professor in the Department of Civil and Environmental Engineering at Princeton University. She's also a professional engineer, having earned her license while working for Leslie E. Robertson Associates in New York as a structural engineer, where she participated in the design of numerous buildings and skyscrapers. Dr. Garlock received her PhD and Bachelor's of Science degrees from Lehigh University and a Master of Science degree from Cornell University. She has received several awards from her university as well as industry awards. And in 2016, Dr. Garlock was the recipient of the AISC T.R. Higgins Lectureship Award on the basis of her work in fire resistance in steel structures. While she was selected based on a series of papers written on fire effects and fire design, this presentation focuses on her work as it relates to engineering practice. We're fired up for this presentation. Welcome, Maria, and I'll let you take it from here.
All right. Thank you, Christina, for that introduction, and thank you to the audience for sitting in on this webinar. So AISC asked me to, in less than 1 hour, talk about what a practicing engineer should know about fire design, and that's a tall order. I will do my best to give you at least some of that information, but the big picture message, I would say, are two things. One is that you have choices, and the other is that you don't need to forego efficiency, economy, and elegance in steel structures for fire protection reasons. Now, if you are, if you're familiar with David Billington or you've been educated at Princeton, you'll recognize that efficiency, economy, and elegance is something that we use to define the best works of engineering. So the best works of engineering, structural engineering in particular, are efficient, economical, and elegant, and they meet that criteria of structural art as defined by David Billington. So what I did was I borrowed that terminology and applied it now to fire design. So you're going to see that come up again a couple of times. Also following with the tradition of Princeton, I'm going to give you just a little bit of background and a little bit of history about fire design. So if we look at the history of fires, we see that fires have actually transformed USA history. So I'll begin with the Great Chicago Fire here. You see a rendering of what that horrific event might have looked like. That was back in 1871. And what we see is about 3 square miles of Chicago were burnt down. On the left is an image of where the Palmer House Hotel once stood, and on the right was the Palmer House Hotel. Now the developer, Mr. Palmer, was heard to have said that this was the world's first fireproof building. And what we say is that there's no such thing as fireproof. Every material has some form of weakness in a fire. So after that event, there was a transformation of building codes. You can imagine that the building codes for fire safety became much more strict, and also a transformation of architecture. So we have this big booming city, Chicago. 3 square miles of it was burnt down, and now there's need to rebuild it and rebuild it quickly. So this is where the steel high-rise building, I don't know if I would say originated, but it grew very rapidly in Chicago in a style, in an architectural style, by these great architects listed on the right, and this style was emulated across the country. Another fire that a lot of people are not so familiar with was a fire in New York City in 1911. This was for the Triangle Shirtwaist Company. The shirtwaist was the women's blouses, the fashion of the time, this white puffy sleeve blouse. And it was a time of sweatshop work conditions. So many young women, mostly coming from other countries, coming on boats to America to work and make a new life, and exploited in a way. They were treated with really bad work conditions, really poor wages. So there was a lot of social unrest at that time. And this fire tipped the scales. After this fire, where about 150 of these young women died, there was a change in politics and labor laws in New York City, and it was the beginning also across the country. And of course, after this, there was changes to building fire safety because it could have, a lot of these deaths could have been avoided with stricter fire safety rules. And then finally, this fire we're all familiar with. This is the events of 9/11, and what you see here is World Trade Center 5. The tree column connections. Research has shown that these connections failed due to the fire, not due to that falling debris. And after this event, I would say that there was a transformation of the way we think about fire design of structures. We as a profession maybe paused for a moment to reflect, how are we designing structures for fire? And it was very similar to how we have been doing it for about 100 years. And should this be the way that we're designing structures for fire? So this event of 9/11 was a stimulus for the structural engineering profession, again, to reflect on how we're designing structures for fire. Throughout this presentation, I'm going to pose a question. When I have a live audience, it's easier to interact with them to draw out that question. So here the question is, do concrete structures perform better in a fire than steel structures? And I've gotten many answers to this question. It's a little bit of a tricky question, and I've in some way answered it already. And it's the idea that all materials have some form of weakness in a fire. And even concrete materials have some form of weakness in a fire. So here we're going to see a video. Let me see if I could play it, of a high-strength concrete beam. There it goes. This is a high-strength concrete girder being subject to a fire test, and concrete tends to spall. So if we have high-strength concrete in particular, low water to cement ratio, large pore pressures accumulate, and what you saw in the video is explosive spalling. It's a bit more dramatic than what you might normally see, but if you look closely, you'll see small pieces of concrete popping out. So steel, concrete, all materials have some form of weakness in a fire. So the outline of this talk, I've already begun it. I've went through some background. Where did we come from? The idea of the history of fire in the U.S. And I will follow up with where are we now and where are we going, or where could we potentially be going with fire design. And the answer to that question, where we could be potentially going, is structural fire engineering, where we see the real response, the real structural response to a real fire. And I have the words real italicized there for a special reason that I'll explain as this webinar develops. Why do structural fire engineering? The answer is in that alliteration: efficiency, economy, and elegance. And finally, I'll end with some conclusions. How is fire resistance traditionally determined? To answer that question, I'm going to ask another question. How do we design a building to resist wind? And if we have this tall building, we need to have it resist wind. We have many structural systems we could choose from. One solution might be to add bracing, for example, to that structure. One solution we wouldn't choose is to put up a tent and not let the wind hit the building. And this is essentially how we design structures for fire. And it's not to say that it's a wrong approach. I think it's a right approach in many cases. But I will also put forward the idea that in some cases we could take down those tents. In other words, in some cases we can let the fire hit the structure and design the structure to resist the fire. So today we use what we refer to as a prescriptive approach to fire design, where designers select materials and assemblies to meet fire resistance using what's called approved methods. And these are qualification testings like the ASTM E119 or computational methods that show equivalence to ASTM E119. And there's many protection systems for steel. I'm not going to describe them. I think most of you are familiar with the different types that are available. And again, coming back to the main point, is that regardless of the system you use, an engineered approach to fire safety is going to lead to more efficient, economical, and elegant solutions. Again, going back to even the bigger picture idea is that you have choices when it comes to how to design a structure for fire. So the next question, does the fire resistive rating imply the time that structural integrity is maintained? Most of the time I get, I would say half the audience doesn't know how to answer that question. And the short answer to that question is no. So I'm going to elaborate on that in a moment. Before I get into explaining fire design, it may be useful to make an analogy to seismic design. So when we're designing structures for seismic forces, we have an accelerogram, a ground acceleration versus time that we input into our analysis. For fire design, it's also a moving demand, so to speak. So here we have the temperature in a space that's changing with time as opposed to the ground acceleration. So in this plot, what you see are different plots, different ways that this temperature in a space can develop, and it will depend on the amount of ventilation you have, the size of your room. It could depend on the thermal inertia of the boundary conditions, and in particular, it will be largely dependent on the amount of fuel that you have in that compartment. The ASTM E119 fire test, the prescriptive approach, that orange line is now superimposed on these other plots. By the way, the pink line represents a full-scale test, and the more smooth lines represent models based on the Eurocode. So what we see with the ASTM E119 is that there's no decay phase in that fire. Eventually, in a space, you will run out of fuel and your temperatures will start to die down. But the ASTM 119 is not intended to be a fire test of that sense. It's more of a comparative test. It's not really a predictive test to predict how your structure will perform. And therefore, it's principally a thermal test, not a structural test. So that's really important to keep that in mind. So the next question is, are there codes or standards that permit anything other than this prescriptive approach that we're accustomed to using? And in the background, by the way, is a furnace where we do some structural testing at Michigan State University. The short answer to that question is yes, there are codes and standards that permit alternatives to prescriptive approach, and I'm going to go over those in a moment. And the alternative is structural fire engineering. Right? So it's essentially performance-based design for fire. So if we look at a performance of a full-scale structure, either in a real fire event or in a simulated event, what we see is that the frames or systems behave much better as a whole than they do as individual elements. So the individual beam will perform differently than that beam integrated in the full system. So in structural fire engineering, the idea is that you treat fire as a load, just like you would treat wind or earthquake or snow as a load imposed on your structure. Fire is a thermal load imposed on your structure. And in that case, you can evaluate systems and components. And also, because you're making this an engineered approach to design, where possible, and sometimes it's possible, sometimes it's not, you can design the structure to withstand the fire rather than protect against it. Again, going back to that analogy with wind, the idea of taking down those tents and allowing the wind to hit your structure. So if we do a side-by-side comparison, prescriptive versus structural fire engineering, one states how the building is to be constructed, the other states how it's to perform. In the prescriptive approach, you don't need knowledge of structural behavior, whereas SFE you do. And then finally, related to that, for the prescriptive approach, the primary role for fire design is in the domain of the architect. It's not an engineered approach, but if you do structural fire engineering, the primary role is going to be for the engineer because it is an engineered approach. So the first step in doing the structural fire engineering is you have to define performance objectives. So those of you that are familiar with performance-based approach to design, you know that as a first step you have to say, how do I want my structure to perform? Then you have to go through and define your demand, so to speak, and that demand is that time temperature curve, that fire model, which will depend on room geometry and fuel load. Then you have to do a heat transfer model. So you transfer the heat of the gases in the room to a temperature on your structural elements. And then finally, the next step would be the structural analysis. So there's one intermediary step that we're not accustomed to here, and that's that heat transfer model. But it's something that several researchers have shown simple closed-form solutions to do that approach. So going back to the original question, do codes and standards permit that? And here we see NFPA 5000 and IBC, the 2012 version here. And the idea is that these codes, as long as you meet the intent of the code, it's permitted. And the intent of these codes is to safeguard public health, safety, general welfare through structural strength, and safety to life and property from fire. If we look at the AISC's document, the famous Steel Bible, as some of us call it, AISC 360, it allows for two types of analysis. One is qualification testing, which is that prescriptive approach I talked about previously, and the other is design by analysis, which is structural fire engineering, referred to in AISC as a new approach to fire, a new engineering approach to fire protection. In addition, there's ASC documents. One is coming out, it should have come out last fall, and I'm told now it's coming out this winter, ASC 716. In the appendix, it's not mandatory, but in the appendix now, if you want to use this approach for fire design, there is an appendix now that essentially states what you should be doing. Now, the how you should be doing what we say you could be doing is a little bit longer to explain. So that is under, right now, development as part of the Fire Protection Committee in ASCE, and hopefully in about a year or so will be available. So the first document, the what, the actual ASC 716 document, is maybe 5 pages long, whereas the how document will be on the order of 100 pages long. All right, so the next question, do we need to consider thermal gradients when we design structures for fire, or can we just assume an average temperature? And the answer to that question is it depends. And the answer I'm going to give you next as an example will be yes, you do need to consider thermal gradients. And that example is for the perimeter of the columns on the perimeter of your building. So this next phase of the presentation will talk about beam columns, and again, in particular, the columns on the perimeter of a building. This image is from a fire that happened in 1991. This was One Meridian Plaza in Philadelphia, where I believe 8 floors were burnt down, and after litigation, the structure was taken down. Here on the left is a plan of one of the structural drawings, and what we've done as part of our study is taken one bay of that floor and analyzed it. So on the left side, you see that's the column on the perimeter, the one that I'm pointing to right now. And what we've modeled was this column and this bay and this second column here to understand how this structure responded in that fire. Now, the structure did not collapse due to the fire, but we wanted to understand the structural behavior. Before I get into that specific case study, I want to just explain generally these columns on the perimeter and how they would perform in a fire. So what we see here is just a generic frame. I've drawn it, it looks like, with simple connections. So this is the moment in blue that develops in that beam due to gravity load. So the beam has a moment that runs through the length, and the column is subjected to an axial load, the column on the perimeter here. When a fire comes, this beam that was subject to moment is now being heated, and it wants to expand. So it's going to push out against the adjacent structures. And it's going to meet some resistance, and therefore now this beam that was designed only for moment is going to be subject to axial load P. And the column that might have been designed only to carry axial load is now going to be subject to a moment M due to that P pushing out against the column. So the idea here is the illustration that when you have a fire, all these members are going to interact with one another because there's going to be a change in geometry due to the expanding and contracting during the cooling phase nature of the structures. Going back to the case study, what we did, we studied that floor area that I pointed out to on that floor plan. The fire started on floor 22, was arrested on floor 30. So we modeled that perimeter frame as the fire growing up the building. And what we found And by the way, I need to say it right up front. We did this study for no fire protection. The structure itself did have properly rated beams and columns. For the purposes of understanding structural response, we removed that fire protection. With the fire protection, this structure did not collapse as it actually showed in the actual event. For this study, we removed the fire protection, again, to further understand structural behavior in a fire. So if we remove the fire protection, on the bottom left we see the failure that we get immediately. This column on floor 22, which is a W14 by 314 column, fails. It's a really stocky, heavy column, and it doesn't fail by lateral buckling. It fails by combined axial load moment interaction. So full plastic yielding through this section is the failure mode that we see in that column. When we plot that full plastic yielding envelope, so that diamond shape on the upper right represents the combination of axial load P, normalized by the yield axial load, and the moment M, normalized by the plastic moment capacity for this section. And we see this traditional diamond-shaped section. So when we plotted now the demand, the actual moment and axial load in the column that failed inside of there, we see two strange things. So at time equals 0, when the fire just starts, we have that first square there. And then as the fire grows, we have on that column the beam pushing out, so the moment is going to grow to the right as expected. But then what happens is the moment completely reverses direction, and with the time of the fire, the data points now fall outside of what we thought was the capacity of that section, and it failed right here at about 41 minutes outside of that envelope. So two strange things we had to look at was, one, why is there a moment reversal? Why is that happening? And two, why are we failing outside of what we thought was the capacity of that section under combined axial load and moment? To know the answer to that, we have to look to the thermal gradients of the section. And we have to look to the idea or the fact that the properties of steel will change with temperature. So on the right, this red line represents the reduction of the modulus, or the reduction of the yield strength of the steel with increasing temperature. So at about 500 degrees C, we have maybe 0.7, somewhere between 0.6 and 0.7% Fy of that steel. And the blue line represents the modulus of elasticity, which will also decrease with increasing temperature. On the left, what we plotted is the perimeter column. So on the far left is the side that has no fire. This is the side that's exposed to the outdoor. So it's a three-sided fire. 5 minutes into the fire, we see that the yield strength of the steel is constant through the depth and has its full capacity at 255 MPa, equivalent to 36 KSI steel. 15 minutes into the fire, the web, which is thinner, heats up faster, so it's hotter, and now it has lost some of that yield strength. So it's on the order of 200 MPa capacity 15 minutes into that fire. And at the time of failure, we see a significant reduction in the yield strength, but we also continue to see a non-uniform distribution of that yield strength through the depth of the section. So just like at 15 minutes, at 41 minutes, the yield strength is no longer constant through the depth of the section. The reason that we had strange results when we first started looking at that is we were using, when we plotted that diamond shape, a constant average yield strength through the depth, and that's what produces that diamond-shaped section. But if we consider that we have non-uniform yield strength through the depth, the actual envelope looks like this skewed yellow line plotted on the right. And what this means is that you are going to have some regions where you actually have more strength than what you think you have, and that's what's happening in this scenario in particular. But you have to be cautious because you also have areas where you have less strength, and that's represented by that red area shaded on the right. what we've done here, I'm going to show you in an animation. The red represents the capacity, that envelope of axial load moment capacity. And this blue dot you're going to see that's going to move, that represents the demand, what the fire is imposing on the structure, which will be moving with every time step, because with every time step we have a different temperature in that section. Okay, now it's playing. So we have, with time, the axial load and moment in that column is going to be changing. And we have the capacity now is also changing. So we have a changing or a moving capacity and a moving demand. And we have to find that point in time where both the demand and the capacity converge. And that will happen, I think, 42 minutes. And there you go. So that's where you find that failure under combined axial load and moment. Okay, so I've answered the question, why is it that we have more capacity than we thought outside the envelope? Now I'm going to answer the question, why do the moments reverse direction? So initially in the fire, on the left we see a little cut of that column that we're looking at, and it's subject to that moment induced by that beam pushing out on that column in the perimeter, which is marked in blue. And then because it's a restrained condition, top and bottom for rotation, we have a moment due to the thermal gradients, due to the boundary conditions of that column. With time, we have the modulus of elasticity that is decreasing the hotter the steel is. So the steel is going to be hotter on the right side than it is on the left side, which means that the left side is going to be stiffer as a material than the right side. So the effective centroid, the center of stiffness, lies to the left of that centroid of the section. And the force resultant, the applied P is, of course, still at the center, but the resultant of that force is going to shift to the left. And what that means is now we have a moment that's acting opposite to the first two moments that we were looking at, that purple or pink line. And that purple or pink line, the moment due to that eccentricity, is going to dominate the response of this section. So those thermal gradients that produce the change in stiffness of the section play a very important role in the performance of that column on the perimeter. And this will be true for any cross-section with a thermal gradient, not just for columns in the perimeter, although this study is based upon that case study of One Meridian Plaza. To give you an example of a case study where this played a role, this idea of the thermal gradients, here's a university building here in the US where for 2-hour fire ratings of the columns, and the columns were on the order of 60 feet tall, so a 60-foot tall column for 2-hour protection was going to cost around $20,000. Thurl Happold was asked to do a structural fire engineering analysis, and they did this. They considered thermal gradients, and in that study they found they were in that red zone, so they had to be careful about those thermal gradients, because if they hadn't been careful they might have overestimated the capacity. But they found that in the end the temperatures were low enough and they didn't need to fire protect the column. You could see on the right how many columns there were and estimate a significant cost savings for that project. All right, the next question is, do structural failures always happen during the heating phase of the fire? So on the right, what we see are temperature versus time curves for 4 full-scale tests that were done in the UK. And do structures always fail when they're the hottest, when we reach the peak temperature, so to speak? And the answer is no, it's not always happening during that heating phase of the fire. And remember again that ASTM doesn't have a decay phase. What we find is that in connections in particular, the failure happens during the decay phase of the fire. So for this segment, I'm going to be talking a little bit about connections. Here's One Meridian Plaza, that case study again where we looked at the columns on the perimeter. Now I'm looking at a connection inside of the building. You see the beams have been shored up, and you see the rip in the connection here. So what happens in these fires, the beam gets hot, it expands, it hangs in that form of catenary. in some cases, and then as it tries to cool, it'll contract, and that contraction will produce significant tension in those connections. So what we did was we studied the performance of these beams, in particular for a full-scale test done in the UK where the data was online, so we were able to validate our finite element studies with that. So on the left is the beam that was, you see, instrumented and studied, and on the right are the results of our finite element study, and I'll walk you through these results on the right to give you the general performance of this beam and this connection. So the beam axial force is plotted here versus the beam temperature. Initially, as the beam gets hotter, the web will buckle, and you could see that on the left by this tension field here that develops, this buckling mode right here. And then as it continues to grow in temperature, it continues to expand to the point where now the bottom flange is bearing against the supporting girder, and so axial load will develop in that bottom flange, and then the bottom flange will eventually buckle. Once you've buckled both the web and the flange, you're going to start to have this beam hang in a form of catenary. So now you see a reversal of axial loads where it's moving towards tension, and during the cooling phase, the dashed lines there represent the cooling phase. We see that we have significant tension that remains in that connection. And this is plotted in kilonewtons. You can multiply that by 4.4 to convert that to kips. On the right, we see the details of what we modeled in this study. So the beam cross-section is shown on the lower right, and looking up top, we see the floor plan. And on the left now, we see the finite element models that we used to do this study. One parameter that we had to be careful about was the slab, because we intended to use this model to do parametric studies. We wanted to run many simulations, and if we included a large model, it would have exceeded the amount of time my student, for example, would have had here at Princeton to do the study. So we decided to model the slab using springs that represented the behavior of that slab, and we calibrated the springs to the performance in the experiments. So these springs, the stiffness is represented by this blue line, and it is considering the stiffness of the steel E, meaning that as the steel weakens in stiffness, the slab is going to have to carry more, so we have an increase of stiffness of that slab. But eventually the slab will start to crack, and the stiffness of that slab will start to decrease again. So that's the rationale behind the form. Getting the proper magnitude of that was a process of calibration with the real test results. On the right, the red are the test results, and if we had kept the spring stiffness constant, it would have been this green line here, which wouldn't have represented the proper deformation of the beam. But the black line shows that by using this varying spring stiffness, we get pretty close to the real results. Here is the model of what the final result looked like, trying to simulate the actual experiment. And we see very similar behavior from our model if we look at the deformations as compared to the actual tests. So we did a series of these kinds of validation studies, felt confident moving forward with some parametric studies. I'll only show 4 of those parametric studies very quickly to illustrate how you can, or how you should look at a connection to understand how the details of those connections might affect the fire performance. So starting with the bolt grade, the actual Carnington test used grade 8.8, which is A490 bolts here in the US, and we changed those size to grade 5.6, so A325, just to see would there be a difference in this fire. And it made a huge difference, where on the right we see by changing it to A325, we have a reduction in the time to failure of that connection and a reduction of the maximum temperature. We also have a change of limit states, whereas now with a grade 5.6, we have shearing of the bolts as a limit state, which we did not have with the A490s. And by the way, when I say failure, I'm referring to the point where the field equations no longer converge. We have like 20% strain in the elements, and the analysis cannot move forward. But at 20% strain, we could feel confident we have reached a limit state The next change we did was we added a web reinforcing plate. The web in this beam is 6 millimeters thick, and the shear tab is 10 millimeters thick. So what we did was we added a plate which is 4 millimeters. So the plate of 4 millimeters plus the web thickness of 6 millimeters adds to the equivalent of the shear tab thickness of 10. And this made a big difference. On the right, we see that the analysis, there was no failure. It ran the full heating and cooling phase of the fire, and a significant amount of tension was carried in that connection. The next study we did the opposite. Instead of adding material, we removed material. So as mentioned, the shear tab was originally 10 millimeters thick. What we did was we reduced that to 6 millimeters to match the thickness of the web. And on the right, we see that this allowed for another 50 minutes or so of time before we reached a failure. Even though the capacity and tension didn't change very much, it was able to endure the fire longer. So I'm going to elaborate on that because it's an important point. On the left, we have a plot of the axial load in that connection versus time, and both designs for the two different thicknesses of that shear tab, the performance is similar, but what's different is that for the thinner plate, it's a more ductile connection because you see that the shear tab and also, although not shown, the web of the beam are deforming with this tension that's going to develop in that connection. And so you have this movement, this allowable flexibility in the connection that allows for more ductility. So one thing, important part of this study, what it showed us was that how important it is for these connections to be able to move, to breathe, so to speak, in this fire where you have a lot of movement going on due to the contraction and expansion of that beam. And finally, I'll show you one more example here where we increase the gap distance here, GH, between the beam and the supporting girder, again, to allow more rotation to happen, more movement in that connection space. But also what that did, by adding that gap, you see on the lower image compared to the upper image, we see less deformation in that beam, in particular in the bottom flange. And so these 4 bolts, when we increase that depth or that distance a little, we're able to carry the load more uniformly between the 4 bolts, whereas when you have too much deformation going on, really 3 out of the 4 bolts are doing most of that work. So that made the difference between the two different results that we have, the end time of 123 minutes versus 165 minutes. All right, next question. Should we design some structural elements without fire protection? And in a way, I've already answered that question, in that we can actually design some structures without fire protection. And this is being done to some extent in the UK. So the image you see here is of a real structure that was built, and the different color beams, dark versus light, represent some beams that have fire protection and some beams that do not. So I'll come back to this case study in a moment. So the research I'm going to present now is not mine. This is done by the British Steel and Colin Bailey out in the UK, and it's related to tensile membrane action, but I think in the context of the theme of this presentation, it's important to present it to you. So tensile membrane action is what you see essentially in this figure. This is a full-scale test where you see the slab and the beams hanging here in catenary. So looking down in plan, what you have is you have a bay where you have protected beams on the 4 sides of that bay, but the 3 filler beams inside do not have any fire protection. And so when the fire comes, these beams soften, so to speak, very quickly in that fire, and this tension field develops, and the equilibrium is found through this peripheral compression ring, so the structure remains standing. It finds a state of equilibrium. And that is the approach that was used to design 5 Broadgate in the UK. That was the image I showed you earlier with those beams inside. And the performance objective was to accept local damage as long as stability of the overall building is maintained. And to do that, they utilized tensile membrane action. Looking down at the floor plan of this building, the beams that are marked in green are the unprotected beams. Those are the beams you saw in that image in the beginning of the slide. And in the UK, as I said, they're coming more and more into this kind of practice of using tensile membrane action. And there was a study that showed it allows us to save about 40% of the fire protection cost using that. And then some cases, like the exoskeleton here, is another example where there was structural fire engineering done to show that there was no fire protection needed for this Hotel Arts in Barcelona. All right, so now I'm going to repeat the same question and answer it in a slightly different way. Can we or should we design some structural elements without fire protection? And sometimes I would say there's no choice. And here I'm referring to, in particular, bridges. Now, it's hard to imagine bridges, why we need to fire protect bridges, where our minds have been on buildings. But if you look around, you start paying attention to the news, more and more often we're seeing tanker trucks that crash against the abutment of these bridges and large fires develop. And sometimes the buildings or the bridges collapse, sometimes they're just left with significant deformation that they need to be taken down. And there was a survey done by the New York DOT that showed that about 3 times more bridges collapse in a fire compared to earthquake. Now, most states, not all, but most states did participate in that survey, including seismically active states like California. So that tells us that maybe we should be looking at bridges to see what we could be doing for them in fire. And the first thing we have to do is understand, how do these bridges perform in a fire? The other thing to note is that the NFPA 502 says that for bridges, critical structural members shall be protected from collision and high temperature exposure that can result in weakening or collapse. But there's no guidelines to tell us how to do that in particular for bridges. For these steel, I'm going to go back one slide. For these steel girders here, the webs are typically quite tall and thin, so they're slender webs. So one critical limit state that we have to pay attention to is web shear buckling, and that's where I'm going to in the next couple of slides. We all more or less understand pure axial loading on a plate, and here I'm using simple supports on all 4 sides of the plate. So you take a plate, simply support it on all 4 boundaries, and you compress it. We can imagine what that buckling looks like. Pure shear loading is a little bit different, and to really fully understand it, you're going to have to go back to your sophomore level mechanics of materials, more circle diagrams that shows you that in a state of pure shear loading on a plate, it's going to happen at 45 degrees to the state shown up top. So 45 degrees, you see that compression. But 90 degrees to that compression, you're going to have a tension that develops as well. So pure shear loading on a plate looks like what I've drawn on the lower left. We know also that beyond that point of elastic buckling, that point where that plate snaps, so to speak, and you have this elastic buckling state, that bifurcation point, beyond that, these plates have significant capacity, and in particular slender plates. So here on the right, we know that the stress distribution now becomes nonlinear, as illustrated in the blue, and we know that a tension field develops perpendicular now to that compression field, and that tension field is what enables that post-buckling capacity, that capacity to carry loads beyond that initial bifurcation point, but not beyond that initial buckling. For pure shear, it's similar. Again, you have to rotate this concept 45 degrees in the state of pure shear, but you also do have now nonlinear stresses acting on the section in compression, and this tension field that enables this post-buckling behavior and the ability of this plate to carry loads beyond that initial buckling state. All right, so that's the background, the theory behind where I'm going next. So with that in mind, we applied this now to high temperature. And what we did was we took a plate with an aspect ratio of 3, and we studied different stiffener orientations, in some part to see if we can enhance the performance, but also to understand the behavior of these plates a little bit better. So in one case, we have a vertical stiffener, VS, On the left, we have no stiffener. Here we have a diagonal stiffener in the tension field direction, and on the blue, we have a diagonal stiffener along the compression field. And the plot is showing that elastic buckling, V critical, for different temperatures of that plate. And what we see is that the diagonal in compression, this blue line, is giving us the largest strength. So if we enhance the plate for the compression field approach, we get better performance. And it's also telling us that the compression is playing a major role in this shear buckling behavior, which is not a surprise because buckling is a compression behavior. If we now go to the ultimate, the post-buckling state, beyond the elastic for these 4 designs, at lower temperatures, having that diagonal in compression shows us the better response. Again, the idea of enhancing it in the compression direction, and also that compression is still playing a major role even in the post-buckling range. But as the temperatures get larger and larger, you see smaller differences between the 4 designs, and that's essentially because the stiffener is softening and is losing its capacity, no longer playing a role in that section. Now going back to how we're going to model this, the AISC specification says that if you're dealing with the post-buckling capacity of a simply supported plates on both sides, what we do is, because of this non-uniform stress distribution on that plate, we can assume we have an equivalent width, shown here, B sub E, over which that stress acts over the plate. So there's a procedure for how to calculate that equivalent width, B sub E. To do this approach for pure shear loading is difficult because we have it acting at a diagonal, and so depending on where you cut that plate along the diagonal, you're going to have a different width. So instead of using the equivalent width approach that AISC uses for the plate shown on the upper left, we're going to use an equivalent length approach. We're going to take a column along the diagonal of this plate and use that column to predict the capacity of this plate under pure shear loading. Now, my intent is to get to the point of elevated temperature, but I can't get to the elevated temperature model until I understand the behavior at ambient. So I'm going to first describe to you how this performs at ambient and then show you how I modify it for elevated temperature. So on the lower left, we see that model. The equivalent length of that column is shaded here in blue. On the upper side, I pull that out to show you what that column, so to speak, looks like. So it has an equivalent moment of inertia. There's this tension field that interrupts that column that goes from corner to corner. And we're assuming that that tension field is perfectly rigid, that there is no rotation at that boundary of the column and that tension field. But we have 3 major challenges. It's a nice model, but the challenges are now, what's the width of the tension field, W? What's the axial load on this equivalent column? And how do you convert that axial load to a shear load? And I don't have time to explain how we went about all of that. This has already been published, and I'll just show you the results. So on the upper right, you see the equation for ambient. The ultimate capacity of this plate at the post-buckling capacity is equal to the elastic buckling capacity, V critical, times that ratio of the length from corner to corner divided by that equivalent length, which is equal to the length minus that tension field with W. The Q sub V is there to account for all the other uncertainties and assumptions that are made in the model. Right now we're using a value of 1, which seems to work well. So the next thing is we have to find W, because to know LE, we have to find this with W. To find W, we calibrated it with 60 finite element models. So we found an equation for W. There's slenderness ratios, aspect ratios, and scale. So we have all the proper parameters in there, and now we have to compare it to full-scale tests. So there's 84 tests out there that we can use to compare our data. I highlight in red set A because set A represents the most common parameters for bridges and buildings that we use in design, and these are the range of parameters that we use to calibrate our value W. So if we set apart set A, which is 27 experiments, we see that our model has pretty good predictions compared to that set of data. If we take the full set of 84, it's still not so bad, but it could be improved by further calibrating W outside of this range of set A. So we take this model as a basis at ambient, and we now modify it a little bit for elevated temperature. And what we modify is this value of L sub E, that equivalent length. So at elevated temperature, we could take LE and modify it to consider properties such as material effects and temperature effects. Again, I don't have time to explain how that was done, but actually just this week I was told Journal of Structural Engineering published this paper online which explains all the details. We compare that now to the tests that were done, full-scale tests. Now, there's not very many tests done for steady-state beams done at elevated temperature. This is the data that's out there, and on the right in the blue, we see that we have, again, a pretty good comparison of our model compared to the experiments that were out there. So this is still a work in progress, but so far the results have been optimistic. All right, so now it's time to wrap up and put everything together. And why do structural fire engineering? And hopefully I've already made that case and answered that question. And to answer that question, I'm going to use as a demonstration the Lewis Library here at Princeton University, designed by Frank Gehry, a famous architect of modern times. Now, we know that architecture today, and here's an example in this image, looks very different than it did 100 years ago. So we have to be careful to apply these prescriptive approaches and other methods that we're used to modern designs. So for reasons of safety, which is related to efficiency, again, efficiency, economy, and elegance is the rationale. Economy, I've explained to you already a couple examples of how we can save money by doing structural fire engineering. And finally, encouraging innovation, because we don't want architects to stifle their creativity because of fire protection reasons, nor do we want structural engineers to not innovate new structural systems because we don't know how to fire protect or they don't fit into the equations, the prescriptive equations that we have. So structural fire engineering allows for safety, cost savings, and it encourages innovation. In other words, this idea, the overarching idea of efficiency, economy, and elegance. And then finally, the conclusions. I will start by summarizing the answers to all my questions, that all materials have some form of weakness in fire, that the fire resistive rating does not imply the time that structural integrity is maintained because it's not a structural test, it's principally a thermal test, and that there are codes and standards that permit structural fire engineering because it meets the intent of the code. Thermal gradients can be important, so I wouldn't neglect them unless you're certain that they can be neglected. And failure doesn't always happen during the heating phase. In particular connections, you have to be very careful of that cooling phase. And then finally, there are opportunities to design some structural elements without fire protection, but it has to be an engineered approach to that design. So the three major highlights is that typical design for fire does not consider structural response, and I'm talking about the prescriptive approach. Structural fire engineering considers the real fire and the real response of the structure to that fire, and SFE offers opportunities to design steel structures that are efficient, economical, and elegant. And I'd like to thank my crew, some PhD students that I list here, who have helped me develop the research here at Princeton, and the sponsors of this research, NSF, NIST, and AISC. And I thank you for your attention.
Okay, thank you very much, Maria. Before we get to our audience questions, we have a quick quiz question just to make sure everyone was paying attention. And to answer this, go ahead and click your answer and then click on Submit. The question is, which of the following is false regarding structural fire engineering? A, in SFE, fire is treated as a load. B, SFE is based on standard fire tests such as ASTM E119. C, In SFE, one sets performance objectives regarding how the structure should perform. Or D, SFE depends on structural behavior, and thus it is an engineered approach to fire design. And you can go ahead and click on your choice and hit submit. Okay, we'll skip to the results here. So Maria, it looks like we have about almost 60% of our participants think that B is false.
Yeah, the answer is B. So in structural fire engineering, the idea of engineering a structure for fire, you impose thermal loads on your structure. So fire is treated like a load, and it's not based on standard fire tests like ASTM 119. It's based on the true response, which is done with an analysis treating fire as a load, and where the performance, you define how you want your structure to perform. So it does depend on structural behavior. So the correct answer here is B.
Okay, great. Thank you. And let's start with some questions from the audience. I'm going to take us to slides, let's say 66. What computer program was used to perform the structural analysis under the simulated fire loading? And what was the time temperature profile used in the analysis?
The time temperature profile was one that was based on the One Meridian Plaza fire. Now, of course, there were no sensors in there to tell me what that actually was. So it was based upon several different amounts of information that we gathered, which was eyewitness accounts of the fire climbing from one floor to another and the timing of that, and also the size of the compartments. And really it was quite an actual large open space, so we adapted that for large open spaces. So when we finished looking at that fire load that we put in there based on One Meridian Plaza, it was as best as we could fit it to the real fire event. Includes the rise and decay phase of the fire. And the structural software that we used Sapphire, which is coming out of the University of Liège, which is a software that is for structure fire. So it has embedded in there the properties of steel at elevated temperature, for example. But through this research project, we also developed just simple MATLAB coding to be able to mimic that behavior without having to use detailed finite elements. So we have published papers that with a spreadsheet even, one can develop both the demand and capacity curves and find that capacity of the member, because we realize that as a practicing engineer, not everyone is going to be using Sapphire or these sophisticated software. So we wanted to bring the research as close as possible as we could to practice.
Okay, thank you.
All the questions?
Yes.
Okay.
And then kind of similar question, what FEM software did you use to run this simulation?
Here we used Abacus, and it looks simpler than it was. So running Abacus using contact elements and lots of nonlinear material and behavior was really hard for my student to do. So it isn't easy. This is not something that that you could just easily program and put in. So again, the idea is that the researchers here, we try to do this here, but then illustrate the concepts or ideas in a way that someone in practice, again, doesn't have to spend hours or months even trying to figure out how to make these models. But this was Abacus.
Okay. Thank you. And then kind of a general question, does structural fire engineering design need to consider fire in combination with wind, seismic, or any other loads in a load case?
No. As far as I know, and the load combinations are in the AISC 360, fire can be done independently of wind and earthquake in terms of load combination.
Great. And then sticking on this slide, we had a question about the bolt grades. When changing the bolt grade and seeing the bolt failure occur, did you say that this meant that the result was a collapse compared to only large deformations with the higher strength bolts?
So with Abacus and the kinds of analyses that we're doing with Abacus, we can't model collapse specifically. So we look to see when the analysis stops running, we have to go back and understand why it stopped running. So it stops running when you reached significant unrealistic strains in your section. So if we were able to simulate it fully, I'm guessing that the lower grade bolts would have sheared off. And actually, that was the stimulus for the Cardington fire test. The tests that we simulated were the second series of tests. In the first series of tests done at Cardington, they found that these bolts did shear off during the actual fire, and it was an unexpected result, so that when they did it again, they monitored that. The first time they had no sensors on there, they didn't monitor those bolts or the connection because they didn't expect that failure to happen. But the second time around, they maybe weren't expecting. Maybe that's why they increased the bolt grade. But we didn't see that kind of failure in the full-scale test. So yes, for the lower grade bolts, the failure, if the simulation ran to physically collapse, would have been the bolt shearing.
Okay. And the next question, is there any research that you know of on the effects of wind or air pressure loads during a fire?
I'm sure there probably is. I'm not familiar with that, but I would encourage whoever asked that question to look for it.
Okay, and then do you know if this approach of structural fire engineering has been done in the United States, and if there are any examples that you can give?
There are companies who are trying to stimulate this here in the U.S. There's not that many. So, I gave the example of Burrow Happold, who brought the job, who's done some work there, and they have now a company here in the U.S. Arup has a special fire group, and they have a small group in the U.S. I showed you an example of SOM. I think little by little, these companies are bringing this learning into their work, but it's harder here in the U.S. to adapt this. It's not something we're accustomed to, and as I said, it's much more common in the UK to do it than here. But there are some companies here who are working on this. SGH is another one, for example. So I'm sorry if I left out any names of anyone in the audience for your company, but I would say generally speaking, yes, there are companies here in the U.S. who do this.
Okay, great, thank you. And then one more question on this series of simulations, the slide that we have up now. If slotted holes had been used in this connection, what effects would that have?
We did use slotted holes. I didn't show you the results. The oversized slots, the largest slots that are standard, are not large enough. So the slotted holes and the oversized holes, they weren't big enough to accommodate the amount of movement that was needed. So we didn't really see a big difference in the results.
Okay, great. Well, unfortunately, that's all the time we have for questions today. For anyone who asked a question that was not answered during the webinar, we will work with Dr. Garlock to respond to you by email.